So good morning, everyone. So we'll just completed our discussion on logic synthesis and verification introduction process. So what are all those? What are the different challenges and how exactly the process is? And as per our discussion, we have already seen that logic synthesis, that means from crude uh, specification to technology dependent or technology independent optimization logic we just need to get from the logic synthesis, and the verification is whatever method we have designed with the help of this logic, whether that is true or not, that is correct based on our requirement or not, to specify that one. Okay, so we'll just proceed towards with the logic synthesis, and later on we'll just continue with the verification methodology. So here in this case, first of all, the complete discussion, okay, is divided into two parts. The first one, it is the logic synthesis with the technology independent design and the technology dependent design. So when we'll just discuss about the technology independent design, there we'll just try to realize the circuit in terms of different gates, okay, or different structural units or different tree based structure. So in this way we just try to find out what are the different nodes which are utilized, what are the transition probabilities, what are the different gates, okay, that can be utilized to design a particular circuit in case of technology independent design methodology. Okay, so there we will estimate about the what are the different resources that utilize for the method. Okay, whereas in case of technology dependent, what we will just go with the that particular technology independent optimization design into different technology dependent design. The technology dependent means either it is a FPGA based mapping, or it is a ASIC based mapping, or it is a LUT based mapping. In this way we'll map it. Okay, so how we'll map it? Based on different industry standard platform like Xilinx or Altera. Okay, so these are the different platforms, or Synopsys, Mentor. Okay, so in this way we will just try to take all this technology independent to some platform where some technologies has been defined, okay, between how we can get the transistor level design. Okay, so in case of technology dependent, there we can get, okay, what are the different that is area unit or the power unit or the delay unit that is utilized for that particular design. Okay, we'll elaborately discuss about this one. First we'll go with the technology independent, then technology dependent, then we'll discuss about the two level synthesis. So already we have a little bit idea, but we'll just need to find out when the number of inputs will get increased. Okay, how this two level synthesis can be performed and what are the different methodology that exist. Okay, and how we can modify this in the future so that our purpose can be solved. Next we'll go with the multi-level synthesis. So multi-level means from two level to the more than two level. Okay, more than two level, that are the different structural unit, that is tree-based structure. So we'll go, okay, or it may possible that some of the layers will just increase to uh, minimize the resource use. Will increase different levels, but the realization methodology will reduce the resources. So our target here to reduce the resources, fine. So one by one we'll check. First we'll just go with the logic synthesis, and then two level and the multi-level synthesis. So again, just a little concept of VLSI design flow. Here in this case, the system specification, then we'll go with the architectural design, then high level synthesis. High level synthesis, it is the C++. Okay, so with the help of this, so we just try to go into the logic synthesis, that is the RTL level. Okay, so our target here to actually find out the optimized RTL, so that that can give us the minimum number of cost factor, that is the what amount of resource, what amount of area, power, delay, temperature, and what the constraint should be minimized, okay, within this particular RTL. Then this RTL is taken into the physical design level, where exactly we used to do the floor planning, okay, floor planning, then placement. Okay. So after that we used to do routing. So this exactly here also, all these things actually we are just estimating in case of physical design. And then after doing all these things, we come up with that is the actual fabrication. So up to this much level, from here to here, everything is based on simulation. Okay, everything is simulation, some estimation method. Okay, so here exactly what we used to do, because fabrication actually cost huge, okay, and it is also not possible to fabricate all the devices. So what we used to do, we just estimate first, and finally when everything is final and everything is just fixed, then we'll go with the actual fabrication. So we, from the physical design, we GDS2 file, we used to give the Fab Labs, okay, Fab Labs, and they used to fabricate the module that is given with the help of this GDS2 file. And then finally, after fabrication, also there may be some fault, okay, within these chips. So that's why the packaging as well as the testing. Okay, so the final product will be launched into the market. So exactly here you can check, this is the one example of circuit. Okay, so what is this particular circuit? From as it is very small, I think it will be uh, understood by you that it is the XOR gate, another XOR gate, AND gate, AND gate, and then we just OR this one. So XOR and this actually gives us the half adder, and then this is another half adder. So this perform as a full adder circuit. So here in this case, so if it is a full adder, then this is another method we you can check. It is the D0, D1, D2, D3. Okay, and we have two signals, select 1 and the select 0, and based on this to select 1 and select 0, you can check D0 is selected when this one is connected and this one is connected. Okay, so this two exactly gives us the select 0 equals to 0, select 1 equals to 0. That means as it is passed with the help of inverter, so it is 1 1, and you are giving this D0, so you will get this particular, okay, output. Later on, this is, it is a 0, it is equals to 1, this is 1, this is 0, and when it this to select 0 and 1 is equals to 1 1, automatically you will get the D3. Okay, so this exactly gives us the information about which particular circuit. Can anybody tell me? Yes, yes, it is a multiplexer. Okay, it is a 4:1 multiplexer. So now it is the normal crude module that we used to learn in case of digital logic design, okay, or the digital electronics. But here, okay, this particular thing will not gives us the solution. So we just need to go inside the particular platform where exactly we just need to implement all those. Okay, so logic synthesis, with the help of this logic synthesis, what we used to do, that is the RTL description. Okay, that is translated into the unoptimized intermediate representation. So first of all, it is a unoptimized. Okay, we check and then we use the different methodology by which we can take some parameter or a single parameter, okay, to optimize that. So how to do this one? We go with some design constraint methodology, design constraint. So we just take the representative form and try to realize it in any other method. Okay, so when this particular thing is get solved, so we can go with the standard cell libraries. Just consider you have one particular it is a module. Okay, so this is a module. So this module can be represented into this two way. Okay, so this is again, it is the m1, this is the m2. So both way can be represented. So we just need to represent it in both way and check all the constraint. Okay, so first constraint 1, constraint 2, here also constraint 1 and constraint 2. So now we just need to check both this. Okay, we just need to find out the cost, okay, based on this constraint 1 and constraint 2 for both this one. So after that, obviously we just need to take some decision. Okay, we just need to take some decision which one is better, okay, based on this cost factors. Okay, this cost factor is exactly, it is the representative fitness factor for this particular design. Okay, so based on our desired constraint. So just consider that your constraint parameter is just to minimize the area. So here in this case, so we are not aware about this area, fine. So we aware only about some product terms, okay, or some cell count or transistor count. So in this way, we just need to reduce the transistor count or cell count or LUT count. In this way, for both this realization, we'll just realize the circuit and we'll just try to check all those. Okay, and later on we just need to come up with one module. Just consider it is a mx, which is just one of this two, which is I'm just considering minimum of m1 comma m2, which is equals to mx. This mx is it is optimized based on some constant. So later on, okay, we'll just do the standard cell library mapping so that this particular mx should be minimum. Okay, it may also possible that a particular standard cell library, okay, these are also not giving us the much optimization. So again, we will check with the help of different other methodologies, can it can all the parameters can be minimized or not. Okay, so this is a simple, okay, methodology what is inside that particular logic synthesis block. Okay, so here we'll go with the RTL description, we'll translate it. Okay, after translation, obviously we'll get the unoptimized, okay, representation. So now obviously that particular translation, the methodology, okay, so any methodology, any here in this case I'm just considering we have one function and we just try to realize it with simple SOP. So in SOP we know that there are different that is Boolean algebra, okay, Boolean algebra, and which can minimize the particular product term. Am I correct? Yes or no? So you just need to apply all those parameter, okay, all those rules, all those properties, so that you can come up with some solution, okay, into the SOP. Obviously after applying the all the parameters or the constraint, whether your circuit will be SOP to POS or it is still in SOP. Yes, so SOP. Yes, obviously it's from unoptimized intermediate representation to, okay, we'll apply the logic optimization. Okay, after logic optimization, we'll go with the technology mapping. It's very simple. Fine. Next, here in logic optimization, how we actually proceed with this one. So initially you must have some input. So these inputs are actually in terms of some Boolean network. Okay. And the timing characteristics for this module should be there. So here in this case, timing characteristics, that means when you are just giving input, so what are the different output you may get. Okay, so based on which obviously the problem is defined. Okay, so am I correct or not? Are you getting them? You have some input. Okay, what are the input? It is a x, y, z. So when you are just giving this input, that is 0 0 0, it is a 0 0 1 0 1 0 0 1 1, in this way. Okay, if you are just giving, okay, this input, automatically in this case it is 0, in this case 0, in this case it is 1, in this case it is again 0. So you must have some output based on all this input. Okay, are you getting the point or not? Then it is a problem. Obviously this is a problem. So here problem does not mean that this is a huge hurdle. It is not hurdle, correct? This is our specification. You can consider this is the problem domain which we have. We just need to minimize it in some parameter or some applying some method. So timing characteristics should be there. Okay, so at a particular instant, what are the different output, you must know this one. So finally, what exactly we expect from the logic optimization? Our circuit should be minimum in area, net list of the library gates, which meets the timing constraint. So within this time period, that means you must apply some frequency. When you are just apply frequency, obviously there is some time slot. Within this time slot, you exactly apply some operation. So that operation need to be complete within this time period. So here in this case, we have this net list. Okay, it is an unoptimized net list. So initially this is the unoptimized, okay, net list. Then we just need to apply the logic synthesis. Okay, so within this logic synthesis, we just inserted the libraries. Okay, different libraries. What are all those libraries? It may be possible that we are using AND or inverter, that is total circuit. Okay, can be realized in terms of AND or inverter. Okay, so this is exactly we have studied at our initial stages. Okay, so any circuit after SOP realization, what you will get? You will get AND or inverter realization only. Now it may be possible that you can use NAND. Okay, what is this NAND? That means we are using two module, or just for your simplicity I am just writing NAND NOR. Okay, so do you know any other implementation methodology other than this AND or inverter universal, other than this? So third I'm just writing, it is the marks based design. Any other? Any other method?
Decoder based.
Decoder. Okay, then now my question arises here. So as you have told me that it is a marks and the decoder, can marks and decoder from our perspective, so we are just not looking inside, looking from the top, okay, what module exactly we have, but we are just looking inside. What is exactly the mask is? This is multiplexer. What is this one? If you just go inside, what is this? Shall I go to the previous slide where we have the that marks realization?
So there
Inverter and
Okay,
inverter
uh,
on and LT.
yes, this is only this one only.
Okay.
Okay, decoder, this is this one only. Yes or no? Okay, so that means, okay, I'm not discarding. So this marks and decoder, these are exactly the part of the first one only. So you are correct. Okay, You are correct that mux and decoder,
the
yes.
different combinations of the universal gate.
That is, I have just considered this one, that is in NAND and the NOR. Okay, either using only NAND, either using NOR, either using NAND and NOR. Okay, either using only AND, okay, OR gate. So in this way, so there are other realization that I think you are not acquainted with till now, that is the AND and XOR is sufficient to realize the all the circuit. Okay, AND and XOR only. Now what is the fourth one? It is the OR and the XNOR is sufficient to realize the circuit. Now next we have the AND and inverter is sufficient to realize the circuit. Okay, so these are the different methods. So I will show you how to realize all those. Okay, so these two part I'm just leaving to you. So just brush up your digital logic design or digital electronics, and you just uh, again brush up your knowledge about how to realize any function. You just take a boolean function and realize the circuit in terms of AND or inverter and the universal logic. Okay, yes everyone.
Yes, sir.
Okay,
Yes,
so
sir.
okay, that will be incorporated, so I'll not discuss anything. Okay, so this is a very basic and fundamental concept, so you just go with your books or internet resources and try to realize any function and go through all the methodology exactly how to realize the function in terms of AND or inverter and the universal logic. So all these parts, remaining parts, are the two level logic, which is my concern. I will help you to learn. Okay, is this okay? Is this okay or not?
Yes, sir.
Everybody,
Okay.
yes.
Yes, sir.
Okay, so everybody please pay attention. Okay, so so here in this case, when we just discuss about the logic optimization, fine, this logic optimization, it is a, already I have discussed that it is a technology independent and the technology dependent. So in technology independent method, we will discuss about two level optimization and the multi-level, and when we discuss about the technology dependent, we will go with the library based, okay, optimization method, that is the FPGA, then different LUTs, then CLB based design in case of technology dependent method. So just jump inside this two level logic synthesis. So in this case, what we have two level boolean function in SOP form. Okay, this is the problem definition, or this is the specification that is given to us for the optimization. So what is our target initially? We will just try to minimize the number of product terms. So when we'll just discuss about the product terms are nothing but these are the n gates. Okay, so minimum, so if we just minimize the number of n gates, that exactly minimize the total number of, okay, gates. Okay, so total number of gates, that they will reduce the total number of transistors. Automatically the primary constant, the primary requirement of the circuit, okay, that is the minimum size to represent any function, that will be fulfilled. So this is exactly the two level, means two levels. So here exactly you can check, we have the AND gates, we have the OR gate. This is one plane, it is one plane, it is another plane. So two planes are exactly, okay, defined for this one. That means we have one plane like this, so this plane will give us some output. Okay, so I'm just considering this is a AND plane. Fine, so from here we will just define another plane. Okay, so this is the OR plane. So this plane exactly gives us the final output. So this final output is exactly based on two levels. So here this two level may get changed, so it is a AND XOR, it may be, okay. So sometime it is the OR plane, okay, and it is the X NOR plane. So in this way, so how to get this one? Okay, so this will be our target in case of realizing the circuit into the two level combinational logic optimization. So this is the basic format for the two level logic, so the programmable logic array. Okay, so here in this case we have, it is a one example is taken. So we have four inputs are in terms of that is the, it is a, you can consider x0, x1, x2, x3, or it is a I0, I1, I2, I3, in this way different input combinations it is just given. So how this n plane is defined with the help of this input, okay, they will generate different product terms with the help of this AND gate. So this is the first AND gate, this is second AND gate, this is third AND gate, fourth, fifth and sixth AND gate. So this 6 AND gate exactly forms the first plane, okay, the first plane, and from here the second plane is derived. So this is exactly the three functions or the three outputs are taken from this two level. Okay, so this is the output 1, output 2, output 3. So three outputs are defined with the help of this. So this is a very simple programmable logic array based, okay, design. So here what do we have in case of input, exactly we are come up with the true solutions, that if we have the three input and the three output, so three inputs are exactly a bar, b bar, c bar. Okay, so these are the all my input. So this all the input they are, this is exactly different AND gates are defined. Okay, and here the OR gate is defined. So this is and this is the OR. So here from here you can check, this is the first function, this is the second function, this is the third function. It's very simple. So here this first AND gate exactly derived with the help of this A and the B bar. So A and the B bar, A, B bar. So from here it is the B and C. Okay, B, C, and from here it is the A bar and the C bar. So these are actually the fuse or the methodology how a particular node is just incorporated into the logic. Okay, so these are actually the plane where already this is predefined. Okay, so it may possible that all these fields is it can be programmable. So based on our requirement we exactly generate different AND gates, and this OR gates are actually defined. So here just tell me, for this particular AND gate what should I write?
A bar C bar.
A bar, C bar. And for this one
A B C.
it is the A, B, C.
Yes.
This one
A bar B bar.
A bar, B bar. Okay, so similarly, and in the second plane also we just need to fuse some portion. Okay, so the first one and second one actually defines the first function. The second function is defined with the help of this two particular, okay, AND gate, and the F3 is defined with the help of this last two AND gates. Fine. So is there any other technique by which we can define all those? Just need to check. So here two level synthesis, also this is the first level, we can consider this is the second level. Fine. So the first level defines with the help of, okay, one single type of plane, so that can be a AND. Okay, so we have considered this the x1, x2, in this way different inputs which defines the output of the first AND gate. So this is AND gate 1, this is the AND gate 2. Okay, so these are the different inputs which define for the AND gate 2, and finally the outputs are defined into the second stage. Okay, that is the two level, this is the first level, this is the second level. Okay, so finally we get the output at the end of the second level. So this is the two level. So any two level, that means synthesis, we have two different stages. first stages gives us the intermediate output. So always we used to get, so just consider it is the x1, this is the x2. Okay, so these two x1 and x2 exactly gives us some intermediate output, and then into the second level the final decision has to be taken from x1 and x2 how the outputs are defined. So this is the only two level based synthesis. But when any function is defined, and we just need to realize it in terms of some more than two stages, so then we will term it as a multi-level implementation or multi-level logic synthesis method. So here you can check, this is one level, this is another level, this is another level, okay, and finally output is taken from this. So what are the advantages of using this multi-level synthesis? Exactly, when we just go for the multi-level synthesis, our product term, okay, or the literal count is getting reduced, okay, in case of multi-level synthesis. So still, okay, two level synthesis why we are studying. So as directly we cannot jump into the multi-level synthesis, obviously this question will arise in your mind, yes or no?
Yes, sir.
Obviously. So because two level synthesis is the fundamental of the multi-level synthesis. Okay, in some of the research it has been shown that if we do initially the two level synthesis, okay, two level synthesis, and then this output is again fit inside the multi-level synthesis, so automatically we get the better solution, okay, better solution. So obviously that still two level synthesis are used in some of the industry standard boards. Okay, so this PLA structures are still used and they are exist. So obviously the studying of this two level synthesis is important, and there will be obviously in our priority. So how to get this, actually this multi-level synthesis? For this we may go with a different structure based decomposition. Okay, so what are all those structure based decomposition? It may be the BDD, okay, based realization, that is the binary decision diagram. Have you heard about this one?
Yes, sir.
Binary decision diagram.
No, sir.
Okay, so this is the first one. The second one, it is the, we can go with the AND inverter logic realization. So as it is the AND inverter, don't think about this one that this is a two level synthesis, fine. So this is the multi-level circuit realization AND inverter. So actually this forms one structure, okay, tree based structure with the help of this AND inverter, fine. And the third one, we have the majority inverter graph, okay. So exactly this is a AND inverter graph, fine. It is a majority inverter graph. So these are the different technique, okay. So we just need to come across so that we can realize the same function, okay, in terms of the multi-level logic synthesis. So in two-level logic synthesis, so this is exactly the distinguish between what is two-level synthesis and the multi-level synthesis. In two-level we have the two-level structure. So in one level, okay, it will give us some intermediate solution, and from that intermediate solution we just get the two-level output, fine. And in case of multi-level, we just need to realize the function in terms of some graph based structure, okay. So, and automatically, and obviously all the graphs having their own minimization methodology, and we just need to minimize based on all those properties. So obviously these properties are not exactly something like it is someone has given. Obviously these are proven methodology. Fine. So this is all about you two level synthesis and the multi-level synthesis, but exactly we have not defined, but you just whether the concept is clear, what is two level, what is multi-level.
Yes, sir.
Okay, in multi-level different levels will create and just try to minimize the number of product term or the literals or all those parameters which exactly define, and it is given in our specification that these are your desired parameters. You just need to minimize all those and find at that particular net list which can gives us this minimized net list for this problem. Fine. So two-level combination logic synthesis. So here in this case, the objective of two-level minimization is to determine the minimum cover of the function. What is the minimum cover? Minimum cover means we'll apply all this property of the Boolean logic or the that is obviously the how the neighboring cell can accommodate, and they can gives us a minimum number of values which can define a particular unit. This is the cover. So just consider you have this f is equals to x y z plus x y bar z bar plus x bar y z bar. In this way, okay, if we define, okay, the product term, so how the neighboring, okay, we just need to check whether they are neighbor product term or not. Okay, they can define the adjacent cell or not. Which are the adjacent cell? Already we have seen in case of Karnaugh map how the variables are adjacent to each other. Can anybody tell me how the variables are adjacent to each other?
One bit change.
Yes, if there is only one bit change between the two successive combination, then we can consider they are adjacent to each other. Okay, so if we will just represent all those function into the adjacent cells, so this adjacent cell have some properties which can minimize some variable from there. Okay, so this is exactly those particular node, if it is that present into the function, so whether they are coming adjacent to each other or not. Okay, that will be our first criteria. Second, first, it provides a means for optimizing the implementation of the circuit that are direct translation of two-level tabular form. Thus, the two-level logic optimization has a direct impact on the micro cell design style using the programmable logic array. So, what is the meaning of this sentence? So, here in this case, if we are able to minimize the particular product term, okay, somehow with the help of some property, so as minimum number of product term is used to represent a particular function, okay, so automatically the macro cell utilization, the final product utilization, that will get reduced. Okay, why? Because this particular product term is actually used the number of micro cell used within this device, so we can realize it and we can get the final output from there. Okay, but this is not exactly the product, okay, which we'll get in our hand. So this is just an estimation based on some technology how we can minimize, okay, the particular problem definition. Are you getting what is the meaning of this one? We will translate it. Okay, the function is given, we'll translate it and we try to reduce some of the parameter, okay, with the help of some tabular method, with the help of some property which is given for the Boolean function, so that the number of cover or the number of product term that should be reduced and we can get the minimum number of there is a circuit to realize a particular function. Okay, because automatically if we just consider for the programmable logic array, this particular product term is exactly defines, okay, the final product of the final output of the programmable logic array. What is the second? The two-level logic optimization allow us to reduce the information needed to express any logic function that represent a component of the multi-level realization. Okay, so that exactly I have just explained in the last slide. that if we are able to reduce the number of product term or some of the parameter into the two level optimization method, okay, so that exactly all the realizations are exactly done into the multi-level logic design. All are in multi-level design. But exactly if we know the two level minimization methodology, and if some of the parameters are can be minimized at the two level, so automatically, okay, the multi level also be reduced, and we are able to find out that particular domain where exactly no more further minimization is possible. So we can look into different parameters so that the further minimization is possible in case of multi level. It is clear, this particular point is clear to everyone. At two level we'll go with some reduction methodology, okay, and that exactly defines how we can proceed with the multi-level. Okay, so just consider you have this particular problem. So within this problem, what happened, some portion can be reduced with the help of two level. Okay, so now you are satisfied with this, yes, this is minimized. Okay, so this output along with the remaining portion we can check into the multi-level. Are you getting the point?
Yes, sir.
Okay.
Yes, sir. Yes, sir.
So the two level logic optimization is a formal way to processing the representation of a system that can be described by the logic function. Hence its importance goes beyond the logic synthesis design. So later on we will discuss about this one. So initially the method by which we exactly take this two level, okay, it is the basic and fundamental way, that's why this is important for us. So we'll take some example to motivate us that how this two level and the multi level exactly help us to reduce the circuit. So till now I think we have a little bit idea about the up to three level or the four variable, okay, logic minimization with the help of K-map. But if we just increase the number of variables, just consider here, okay, what is the motivation for us? So there are many functions that are too expensive to implement in the two level. Okay, so how, just consider, so 16-bit adder, if we consider for the 16-bit adder, so obviously 32 input lines will be there. Am I correct or not? From the A it is the 16 lines, for B it is 16 lines, okay, and 2 to the power 16 is the product term that will be available for this one. If output may be 0, output may be 1, based on which, as it is a 16-bit adder, automatically, okay, 2 to the power 16 outputs are. So now tell me, okay, so realize this one into the two level, obviously 2 to the power 16 product lines, so it will be very difficult for us to exactly realize into the programmable logic error. So two level functions, so here it is given, so f1 is equals to ab plus ac plus ad, so this is one function. For f2 it is the a bar b plus a bar c plus a bar e. Okay, so here in this case you can check what is the total number of product term. Okay, all are different, that's why 6 product terms. Okay, and all the product terms are not we can share among this one. Okay, and if we just check, as it is a 6 product term means 6 AND gates are there. So if we just translate it, okay, so each AND gate, if you just realize, so at minimum 4 number of transistors are required, okay, to implement this one. So minimum 24 transistors are required, okay, CMOS transistors are required to implement this particular function. Are you getting this one? Yes or no?
Yes, sir.
Okay, you
Yes.
have two functions, f1 and m2, two functions, and each functions having 3 product terms, so total 6 product term, and from the output, okay, we can observe that yes, no product terms are shared among each other. So if we just try to realize it in terms of transistor level, so 1 2 input AND gate, it can be realized with the help of 4 transistors, so total 24 transistors are required Okay, it is a lump sum equation. Okay, so but if we just try to realize it somehow, okay, and some that is product terms or some parameters, if we extract, and this can be shared between these two functions f1 and f2, so automatically the function can be reduced. So here in this case, what we have considered that k is equals to b plus c. Okay, k equals to b plus c. From this first function I am just writing f1 is equals to, okay, so from here if we take a as a common from these first two, okay, first two product term, so it is the b plus c, then ad. From here also, from function f2, if we just take common a bar, so it is the b plus c, and then a bar e, correct. So from here what we have observed that if we realize somehow b plus c, so the b plus c is exactly uh, a particular stage, okay, which is common between these two functions. Okay, then so this is b plus c, so this b plus c can be utilized for the function f1, for the function f2. So this is the a, so here you can check this b plus c is a single unit, okay, and here one AND gate, another AND gate, one AND gate, and AND gate. So how many AND gates are used now? 4. 4 AND gates are used. Oh yes, and but here we have inserted one OR gate in between to just omit 2 AND gates. Okay, so but we have to think that we just need to realize this b plus c first. Okay, then this b plus c is exactly one label that is inserted in between, okay, this a and the ad, a bar and the ae. Okay, so exactly, so what is that particular b plus c is here considered as a k is equals to b plus c. So f1 can be realized as a ak plus ad. So here in this case it is the a, this particular b plus c is a k plus ad. Here in this case it is the a bar k plus a bar e. So this is the realization. So in this way, what we have inserted, we have inserted one particular label, okay, to realize this one. So from here how many AND gates are used? 1, 2, 3 and 4. Okay, 4 number of AND gates are used. So here in this case if we just check, so 20 transistor in static CMOS, okay, and we are not considering any, that is a inverter, okay, as it is a bar is present here, a bar, so we are not counting, so that's why okay, so only 20 numbers of transistor are used by inserting one label. Okay, so that particular label is b plus c, fine. So b plus c is a label that we have just inserted somewhere so that this particular, okay, number of counting or the transistor, okay, that can be reduced. So this particular motivational example is clear to everyone. What we have for two label, yes, for two label we have different functions, boolean functions, okay. So this boolean functions is exactly that it will be represented with the help of different AND gates and the OR gates, okay. So based on this AND gate and OR gates, obviously the number of transistors are defined. So somehow if we just reduce one AND gate, so this AND gate can reduce 4 number of transistors. So now think in this way, if this 2 to the power 26, this number of product terms are used, so it is a very huge number that actually expands our cost of production. So somehow if we just reduce this 2 to the power 16 to the 2 to the power 10, obviously, okay, the number of transistor is reduced. As the number of transistor is reduced, so that means total number of, okay, sorry, the number of product terms are reduced. So as the product terms are reduced, that means total number of transistor is also can be reduced from this one. So that's why the multi-level realization is important. Okay, so here is how we exactly define the Boolean functions. Okay, so if we just consider the Boolean function is represented with the help of zeros and one. Okay, so if this two variable Boolean functions need to be realized, so this Boolean function 0 and 1 that can be realized in terms of either 0 and 1 for one variable, so 0 and 1 for another variable. So this two variable exactly defined with the help of 0 0 0 1 1 0 1 1. Okay, so from the Carnot map we can check for the particular one bit. Okay, so for one bit one cell is there, for 2 bits, okay, this bit is represented with the help of two adjacent cell. Okay, either it is a 0, either it is a 1. When two variables are there, okay, two variables are represented with the help of 0 0 0 1 1 0 1 1. In this way we can just represent, okay, all these cells. If we have the three variables are, okay, if we just consider this the x y z, automatically all these representations are exactly how, okay, we have already seen that they are adjacent to each other, 0 0 0 0 0 1, okay, in this way. Okay, so for four variable this is like this. So it is how, okay, we have represented and how we can just, okay, realize the Carnot map after the four variables. Now for this one, if we just realize into the Boolean space, we just want to realize all those cells or all those product terms into different node realization into the hyperspace. That means within the space I just want to realize it, okay, into the three-dimensional space. So when it is just a single bit, so the single bit, okay, so this is the single representation, but when it is just represented into zeros or one, okay, so now it is oscillated between these two. Okay, either it will be in this position or either it will be in this position. Okay, that we exactly represented in case of different cells, either this particular variable into the true form, okay, this is the true form, or either it is into the complemented form. Okay, so just consider the variable is x, so it is a x bar or it may be a x. So here also it is the same within this Boolean space, so it may be a x bar or it may be a x. So when the two variables are there, just consider x and y. So obviously this x and y we are able to represent it with the help of this K map. So this can be realized with the help of this hyperspace into, okay, into this four dots. Okay, that is the it is exactly the x bar y bar. We can consider this is x bar y, this is x y bar, this is x y. So in this way different, okay, product terms are represented into the Boolean space. So for the three variable it is a three-dimensional structure, and when it is a four variable, so such kind of cascading hyperloop is created in between. Okay, and we just need to consider that all are, so here, okay, this particular, this variable and this variable is adjacent to each other, because you can check, okay, you can check thus this variable and this variable exactly differ by only one bit. So it is a y bar, it is a y bar, so it is a x bar, it is a y, so only x is just getting changed from 0 to 1. Similarly from here to here it is a x to x, no change, x y bar to y, so only one variable. But here from this particular point and this particular point, these are not adjacent to each other, so we are exactly not able to make any cover between these two. Okay, because x is changed to x bar, y bar is changed to y, so these are not adjacent, so we are not able to make any cover in between. So if we are here, just consider we are here, so this particular point is also adjacent, this particular point is also adjacent, this particular point is also adjacent to each other. Okay, so in this way here also, okay, this is adjacent to this one. As the number of variables are getting increased, so the space, the boolean space, this all these boolean representation of this particular variables are getting adjacent to each other. So as they are getting adjacent to each other, so we have more number of transformation product terms, so where we can just travel. Okay, and we can take, why, just consider when you have x y plus x y bar, so from here you can take x y plus y bar. Am I correct, everyone? Am I correct? Yes. Now if you have x y plus x bar y bar, can you do anything? Can you do anything?
No, sir.
No. Okay, if just I'm just increasing number of variable. How? Just consider a b c d plus a b bar c bar d plus a b bar c d bar. So in this way, if the number of variables are increased, now you can do at least a little manipulation or some modification inside it. Am I correct or not? So as the number of variables are increased, so number of this particular nodes which are adjacent to each other is getting increased. So as these are increased, so we have some probability to take them into the multi-level synthesis. Okay, so but are we able to do it in case of two-level synthesis? Yes, we can do it, but the complexity of the system is getting increased. So as the number of variables are getting increased, so how to do this one, how to solve all those, so how to take, so as from the 4 variable to the 5 variable, so have you done any k-map realization for the 5 variable?
Yes, sir.
Okay, 6 variable, 7 variable,
No, sir.
8 variable? No, as the number of variables are getting increased, so with the help of k-map, okay, it is very difficult to realize. So we just need to jump towards the heuristic method. Okay, heuristic method. Okay, so this heuristic method, exactly what we used to do, we just need to travel towards this particular node and try to find out whether it is covered or not, whether this particular node is adjacent to it or not, and if it is adjacent, so we try to cover it like this. Okay, and we'll just move into another direction, okay, from that particular node, and try to make maximum cover as much possible from a particular node. Is this clear, everyone? Okay, this is exactly done in case of Espresso tool. I'll discuss later on. Okay, what is Espresso tool? So
Sir, I had a doubt regarding the.
Okay, sir.
Yes,
Yes,
sir.
sir. Okay, sir.
just wait.